Okay, today I'm going to talk about Gibbs free energy and the connection of thermodynamics to equilibrium. So Gibbs free energy is the determination, the ultimate determination of whether or not a reaction is spontaneous. And so Gibbs free energy is equal to the enthalpy minus the temperature times the entropy. Now, this is important because the units of Gibbs free energy are in kilojoules per mole of Kelvin. And that is also the, or kilojoules per mole, I apologize. Delta H, or enthalpy, is in units of kilojoules per mole. And then entropy is typically in units of joules per mole Kelvin. And so you have to take away the Kelvin part of this term, so you multiply it by the temperature. So this equation is fairly useless, right? Because we don't ever need to know the Gibbs free energy of a system. We need to know the change in Gibbs free energy. So you go down here to this equation that uses the delta, which is final minus initial, right? The change in Gibbs free energy. And that is equal to the enthalpy change minus the temperature times the entropy change in a standard in a situation. So this equation works for any system, and then if you have standard conditions, you put the little zero up there, and that little zero indicates that you are at standard conditions, which is 298 Kelvin and 1 atmosphere of pressure. And so when you're calculating free energy changes, you can look up the delta H for a situation and the delta S for a situation, and then you can see how they play out together. So in this situation, we have nitrogen and oxygen making two nitrogen monoxide gas molecules, right? So you have two particles here on the left, and you have two particles here on the right. So the entropy change is positive, and the enthalpy change is positive. So they're kind of competing against each other, right? So you want to see who wins in this situation. And so when you calculate it out and you put in the numbers in there, notice that you have to convert the joules per Kelvin for the entropy value into kilojoules. And so this is your little conversion factor. You're moving the decimal point over 3 spaces to the left. And so when you do that, you can see that the entropy change is not nearly as great as the enthalpy change. And so enthalpy wins, and this reaction is non-spontaneous. The other way you can calculate Gibbs free energy, because it's a delta, you can also do the products minus the reactants. And so that's very helpful. The fact that they are all state functions allows you to do this, right? So all thermochemistry equations or thermodynamics equations are generally final minus initial or products minus reactants. And it does matter how many moles you have. That's what this N and M are in this equation, are the moles. Okay, because moles, the amount of reaction matters. And so let's say you had a situation here where you're trying to calculate the standard free energy change for this reaction, and then you are asked to do for the reverse reaction. Okay, so you have to look up the values in your Gibbs free energy table, right? You have to have a thermodynamics table for this. Okay, so when you look at this, the chlorine gas is in its standard state, right? Chlorine gas, chlorine is a gas at standard temperature, right? But phosphorus is not a gas, right? Phosphorus exists as a solid in standard state, and so you have to make a conversion there. And so what you do is you take the values from your standard and thermodynamics table, 4 times the value of PCl3, because there's a 4 in front in the equation, minus the reactants, right, minus your P4, your phosphorus, and minus 6 times your chlorine, right? And so that would be 4 times this value, minus 1 times this value, and overall your reaction is thermodynamically favored because you have a negative delta G. So this equation is great to figure out, like in general terms, how is your reaction going to be favored? So in what situations will your reaction be favored? If you have a negative value for delta H, right, that is what is thermodynamically favored. And if you have a positive value for delta S, that is favored. And so if you see that you have a negative delta H and a positive delta S, then this reaction is always going to have a negative delta G value, so it would be spontaneous at all temperatures. If the opposite is true and you have a positive delta H, or if you have an endothermic reaction, and you have a negative delta S, or a decrease in disorder, then you're always going to have a positive delta G, right? Because that's going to be the opposite of the first situation. But what happens if you have an exothermic reaction with a reduction in entropy? Well, then it's going to depend upon the temperature. It'll be spontaneous at low temperatures when this T delta S term is low, right, has a low value. And then it'll be non-spontaneous at high temperatures when this T delta S term has a large value. Same holds true for when you have an endothermic reaction but an increase in entropy. Then that's going to be spontaneous at high temperatures when this value is a great value that can overcome your delta H value, right? And so here's some examples of this. Notice that liquid water becomes a solid at low temperatures, right? Because that's when water freezes into ice. But at high temperatures, that's when ice melts into water. So here's how this is related to equilibrium. Okay, so the delta G for any situation is going to be equal to the delta G at standard conditions plus RT times the natural log of Q, Q being your reaction quotient, right? It's the products over the reactants at any point in time, right? RT, this is interesting, I think, that the gas law constant comes into play here. You don't have to necessarily be dealing with gases for this equation to be used. And that's really, I think, kind of the beauty of this R gas law constant, is that it can appear in situations where you're not using gases. Now note that it says T is the absolute temperature meaning that it's a temperature in Kelvin, in units of Kelvin. And so if you're at a situation where you're at equilibrium, right, the delta G would be 0 because there's no advantage to going forward or reverse, right, because you're at equilibrium. And so at equilibrium, delta G equals 0, and the Q turns into K. And so delta G plus RT times the natural log of K equals 0. So if you rearrange that equation to solve for delta G is equal to negative RT times the natural log of Q, or of K, I'm sorry. And so this is how equilibrium can be related to the Gibbs free energy, right? So if you have an equilibrium value that is above 1, that means that the reaction favors the products, right? It also means that it is thermodynamically favored. Okay, and so you can calculate K based on your delta G by rearranging this equation and solving for K, and then K is equal to E raised to the negative delta G over RT. E meaning the that key on your calculator, the E key, right? And that's it. All right, that's all that we have for you. So now you should be able to do all the rest of these thermodynamics book problems, right? I scrolled down past the ones that you already did, right? You already did 49. And so we're going on to 53 and to the end. And so you should be able to do this. This is the delta G equals delta H minus T delta S equation. And many of these are the same, right? And so you just keep going, keep going, keep going, and then you're at the end with number 75. So rock these out and let me know if you have any questions.